We've seen deterministic finite state machines. Let's look at non-deterministic finite state machines, where we're going to add non-determinism as a feature, and we'll see that that's going to let us write more complicated machines, or at least write them more easily, but it's a more complicated model to deal with. And then we'll try to formalize those concepts. Okay, so here's just an example of a non-deterministic machine. This one's somewhat involved, but we'll jump right in. It looks like a regular finite state machine. Let's consider the input ABA, ABA. Okay, so you come in and start state, you see an A, it's a little self loop here. You see a B, and two choices. Non-determinism says you might take either one of them, and if some path can accept the string, then we're going to say that's this whole machine accepts the string. So let's go A. Let's just try this one. I don't know what to try. B, A, and then I'm sitting in state 4, and I see another A. Ooh, and there's no transition at all. Okay. By the way, non-determinism is going to say, hey, we're going to relax the transition function to simply a transition relation. Okay. So what's the difference between a function and a relation again? One input might be related to several, outputs. So state 1 on a B might be related to 2, and state 1 on a B might be related to 3. Similarly, there might be nothing associated with a particular input. State 4 on an A might not be related to anything. That's kind of like a fail state. But all we're going to do, the only difference between deterministic and non-deterministic formally is we relax the word function to the word relation. And we have to then worry about what it means to accept. So, where were we? If I try A, B, A, and then I'm stuck. Okay. Of course, I could have tried A and then a B, and then I could have taken this loop on A, and then I see a B. Oh, there's an arrow out of here on B. This arc here is, this label B goes with this arrow. Hard to tell, but B, and then I'm sitting here, I see an A. Great, I'd end up. Oh, but I'm in a state, it's not an accept state, and I exhausted my full 6-character input. Okay, but there's one more path we can take through here. I've looked at this. I'm pretty sure there's only one more. I can go A, self loop, B down. A is a self loop, have to do that. And then another A, and then a B, and then an A. I can reach state 4, and therefore we'll say that this whole state machine accepts the string ABA, ABA, because there's some path that accepts, okay? I'm not saying every path accepts, but some path accepts. So, the other thing we're going to add to non-deterministic machines is the idea of an epsilon transition. I already mentioned that we're going to make it a relation that has 2 or more possible transitions or no transitions. We're also going to say, hey, if you want to if you're in one state and there's a transition marked epsilon, the empty string, yeah, you can go from state Q0 to Q1 without reading any input, okay? So that's the second thing we're going to add to make a machine non-deterministic. Okay, so, and by the way, if you want to think about, gosh, do we really need epsilon transitions? Can we do it just by relaxing the idea of relation, but not introducing epsilon transitions in the future after seeing a few more slides? Yeah, you can go back and think about if that's equivalent, or maybe vice versa. Can I change epsilon transitions, use only epsilon transitions, but not a relation? To think about later. Okay. And so in the slide here, it just says, hey, Q0 on an A could lead to Q2, could lead to Q3, or Q0 might go to Q1 without consuming any input. And if Q1 on an A does something, we'd be free to wander off there. Okay, so again, what does accepting mean if some path accepts? Okay, not all paths. In deterministic computations, there was only one path. Deterministic machines. Now we have many possible paths. If any one of them accepts, we say the entire string is accepted. So, okay, so we already saw this. The fact that you have non-accepting paths, the fact that you have some paths that get stuck and don't have an output, yeah, they don't accept, but maybe some other path does. Okay. Other paths don't matter. Okay. We'll talk about, once we have a machine, a non-deterministic machine, we'll talk about the language of that machine, same definition we had before. The set of all strings accepted by that machine, but we'll just let our machine be non-deterministic and updated what it means to accept. Okay. So you can look at this and say, what is the language of this machine? If you want to pause a second and do that, I'm not going to walk through in the video, but you can say, hey, pause this. What is the entire language that this thing accepts? And I'm going to kind of give it away here right now. No, right now. It turns out all strings that end in an A. Pretty complicated machine to do that. There's simpler machines that will do whose language is the same as this. But it turns out state 1 accepts strings that are entirely A. You just start here, you read 0 more A's and no B's at all. Okay, so that leads you in state 1. You can figure out that whether you have an even or odd number of B's in any sort of chunk, you can end up in state 2 after either an even number or an odd number, and then end up in an accepting state. If, by the way, so I can look at the string BBBA, where I know there's an odd number of A's, I kind of know this. I can take this transition up here, and then this pair of transition BB is going to bring me back to 2, and then my final A will bring me here. But notice that in advance, if I don't know there's an odd number of B's, which I, in general, as find a state machine can only look at the one next character of input, it doesn't know if it should take the odd path or this one, which is an even number of B's to get to state 2. I should say an even positive number of B's, I guess. So, okay. Okay. So one way to think about this, I'm going to call it the finger approach. And this is going to be a little bit weird. Let me just sketch this real quick here. This machine in my paper. I'm going to have state 1. I'm just going to draw the states without all the arrows necessarily, because you'll have the much better looking screen to start with. But if you go ahead and say I have something like this here, I'm going to start in state 1 and look at that ABA. Okay? So starting in state 1, I can take an A. I think I have to do that self loop, right? So, great, do a little self loop. Then B, I can either go over to state 2, if I can do this, or I could have gone from state 1 down to state 3. So now I need sort of 2 fingers on this paper to keep track of where I could be, okay? And now, so I've read 1A and 1B, and I see another A. This one up in state 2 is going to do a little self loop, okay? The one down here in state 3 is on an A, it's going to do a self loop as well, okay, great. And now I read another A, and they both self loop. I still have 2 fingers about where it could be. Now I read another B, and what happens? The 1 and 2, this finger could go down to state 3. This one that had been in state 3 on a B could either go up to 2 or 4, right? So I have, out of this finger here, I think it was, this one's here, this finger goes up, oh my goodness, this is a mess, especially with the glare of the sun here. At this point I can be in state 2, 3, or 4. So I have fingers in 2, 3, or 4, and I'm just going to go ahead and just reset my fingers to be 2 or 3 or 4. Okay, so I have 3 fingers going on, and I still have 1 more character to read, an A, at which point this one goes in a self loop. This one is that right? I want to accept on an A. Yeah, oh yeah. So what happens, this finger here that is off in state 4 on another A dies, okay? So I'll make my hand be more polite here. That hand dies. 3, reading an A, the finger that was there goes in a loop, comes back to A. And this finger here that was in an A can now go to either self loop or back down below to 4. So now I have fingers again in states 2, 3, and 4 after reading that A. And then I'm done with my input. Do I accept? Yes, because one of my 3 fingers was in an accept state. Okay, so that's another way of thinking about computing with a finite state machine, following all the possible paths. And you have a little finger on every state you might be in, and you might need more fingers. Fingers might, You might need fewer fingers after another few steps. And at the very end, okay, I read my input, here's all the states I could be in, is one of those an accept state? Well, that means there was some way for some finger to reach the accept state. Okay, so let's look at this. So first we're just going to define a language. Let's read the logic of this language. Let L1 be the set of all strings W such that there exists a string X that W equals X concatenated with the letter A. Oh, that's all the strings ending in A. That's the machine. We had a machine for that. We just barely wrote it. Okay. And so now you can look through. I'm not going to do more accepting paths. We already looked through an accepting path for ABA, ABA. You can look through for these other accepting paths here. The first one will have accepting paths. The second two, a single B, should not have an accepting path or nor BAAB. And I'll let you step through that diagram yourself and assure yourself. The B is pretty easy to find that, yeah, no path can go there. You're either in state 1 or 3, I think, and you're done, so you're not accepting. This one you have to, again, look at all the places you might be after seeing BAAB, but it turns out none of them are accept states. So, okay. One of the nice things about a non-deterministic machine having a relation is that you don't need to fill in every single transition. If you leave off a transition, that's essentially going to a dead state, and so we don't even need to include it in our model, an explicit dead state that we think of as a dead state. It just sort of falls out of a definition of non-determinism. There might not be anything related with your current state, comma, input. That configuration, remember that term, configuration of a machine? The current state and the remaining string to read. Okay. So let's think about concatenating two languages. By the way, let's just think about what these languages are, and then we can think about building a finite state machine for it, or a non-deterministic one. Let L1 be the set of all strings that, it's the same one as before, all strings that end in A. That is, there's some string of A's and B's followed by A, that's my string W, and yeah, it's a set of all W that do that. What is L2? Pause for a second, think about it. Okay, you're back. Set of all strings W such that there is some string X, just X is in A, B star, some string of A's and B's such that W is A followed by X. Okay, well that's all strings that start with A. Well, let's go and find a non-deterministic machine first for L2, then for L1. So I'll give you a moment to do that. I'll give you a hint. L2 is easier. In fact, it can be done with a deterministic machine. L1, let's get a bit more clever. So give me a non-deterministic machine for L2, and then a non-deterministic machine for L1. Pause and do it now. Okay, so looking at this, I'll say that here's my solution for L2 first, okay? And it's not so bad there. You look at it, and we see, what do we got? A machine M2 such that the language of M2 is L2. Okay, just C and A, and after we C and A, we go to the end state and can read whatever we want, and we'll end up in the M state, because that was a string that started with A. I don't have a transition for B from that first state, because we're non-deterministic. I don't need a fail state. If I wanted to make this deterministic, it'd be super easy, just add that fail state. Okay, I should say, by the way, every non-deterministic machine is perforce an example of every deterministic machine is perforce a non-deterministic machine. That is, if you have a function is a relation with extra conditions on it, right? So every function is a relation. So yeah, so the transition function is a transition relation, so the deterministic machine is a non-deterministic machine. It's sort of a degenerate case of a non-deterministic machine. Doesn't use any non-determinism, but still counts. Okay, how about L1? That was a more clever one, wasn't it? To use here's where we really use non-determinism. I'm going to go ahead and have my L1, and here I'm going to go ahead and say I have a machine that sits there and loops in state 1 over and over and over again. And then whenever it chooses, when it sees an A, it probably loops back to itself, but if it chooses to, it can go to state 2, the accept state. Now, if you're lucky and you choose right, you will choose the first transition to a self almost every time, but then when you reach the end, not knowing you're at the end, but if you're lucky and guess, hey, you just happen to go to that other state and you finish the string in an accept state. So that's an example where this machine is easier. We could also write it as a non-deterministic machine, but kind of easier and elegant and cute to write it as a non-deterministic machine, L1. Okay, now, next question, L3 and L4. L3, I think we looked at that, did we? What is L3? The concatenation of L1 and L2? It's going to be, hey, a string from L1 concatenated with some string from L2. Well, some string ending in A concatenated with some string beginning with an A. So yeah, we go ahead and say, hey, it's a set of all strings such that there exist other strings, X and Y, big long strings, such that W is a big long X followed by a single A, followed by a single A, followed by some other big long Y. Notice that this X and this Y need to be different strings. I can't say XAAX, that'd be something else. It doesn't have to be the same string at the beginning and the end. It just needs to be any string from L1 followed by any string in L2. In this spec here, X was a local variable. So this X is not the same as that X on any particular, when you pull out random strings for each of those two sets. Okay, so yeah, this is just, go ahead and write a non-deterministic machine for strings that contain an AA in the middle of it. That's what this ends up being, okay? And then we'll go ahead and look at L2 concatenate L1, not the same language. Some member of L2 starts with an A, has a bunch of stuff, and then concatenate with some string that is a bunch of stuff followed by an A. And by a bunch of stuff, it could be 0 characters. So yeah, it means we have to have A followed by a bunch of stuff followed by another A, where it could even be, if I'm just taking the string A from each of these languages, I'd get the string AA, which is in the concatenation. So yeah, this is maybe even a little bit easier to write as a machine. Give me finite state machines for L3 and L4 using non-determinism. You can go ahead and pause. And now you're back. Oh, actually, no, I need to pause so I can write it in my own notes here. Let me pause. Wait, how do I even pause? Pause, okay. Great, so here's my L3. I'll look at it here with you. We got this one here. And, it's not too bad. Let's go ahead and read about, we're going to use that same trick we used for L1. Read a whole bunch of A's and B's. When you feel like it, skip over, when you see an A, skip over to that second state, okay? And you're sitting there, you've read one A. Now we read another A, we get to here, and now just keep reading the rest of the input. Notice I don't need to worry about when I see B backtrack or anything like that. I could do that, and we would in the deterministic case, but I can just sort of say, hey, I'm going to rely on non-determinism. If there is some correct place it could make that jump, if there is some computation that could reach an end state, then we accept. So I'm making my life easy. I'm not worried about having to keep track of exactly which parts of a substring I've already seen and backtrack to the right place. I'm just saying, hey, keep reading until you reach the part of the substring and magically guess that you're about to get there. And if there is some way to guess, luckily, then our machine, we call it accepting. Okay, great. So that's L3. L4 is similar. I'll leave that to you. But I want to point out something interesting about L3 in comparison to L1 or L2. If you take L1, so we're looking at the language of L1 concatenated to L2. Take the machine for L1, and when you get over here and you reach the end state, let's go ahead and just say, hey, now I'm in this state. I'm going to magically now make an epsilon transition, which I can take without reading any input, and go down to the machine for L2 and land in here, which is L2 start state, and then just continue reading it. Hey, I went ahead, and that gives me, and if you look at that, that's kind of what we have here. I sort of merged the end of this with the start of that, but if I go ahead and just make two states here connected from between this A and another state that has an outgoing A, and I connect them with an epsilon transition, I'll draw that. I'll just go ahead and draw it in a moment. Then, yeah, we have a non-deterministic machine to do it. But here's the cool thing. We made that non-deterministic machine without really thinking. We just took the machine for L1 and then the machine for L2, took M1 and M2 that we already had built, and just connected them in a really blind way. And what does that show us? It shows us that, hey, if you have any two languages accepted by a non-deterministic machine, like M1 or M2, the language of M1 concatenated with the language of M2 gives us, we can make a new non-deterministic machine for that accepts exactly the same languages. Okay, and I'll call this new machine M3 prime, and let me put an equal sign here. And I'll claim the language of M3 prime is the same as the language of L3, and it's again just what I did using that non-deterministic state. Loop around, we need our first A, and then instead of what was the final state of L1, we take an epsilon transition, over here, and then we take an epsilon transition to here, and then we do all the stuff that L2 needed to do starting from L2 start state. So yeah, and that needs to be a accept state, that very last one. Notice as a shortcut, I'll go ahead and we can do this in the deterministic machines as well. If you have an arc for A and an arc for B that do the exact same thing, you can just draw one arrow and just label it with A and B. Let's not make our life rough on ourselves. Okay. So, not only have we shown machines for this, we have now motivated that the concatenation of two non-deterministic, or two languages each recognized by a non-deterministic machine is itself can be represented as another non-deterministic machine. With actually sort of sketched a construction of how to do that. I'll let you try that for L4 and see how it goes. Okay. So, and union of languages. Okay, what's the union? Is again the union of two sets, a set of all strings that end with A and the set of all strings that start with A. Can you write a non-deterministic machine who is the set of all strings such that either they start with A or they end with A? Yeah, go ahead and give that a try. Go ahead and pause. Hint, let's use non-determinism in a really, again, clever way. And I'll do it. I'll be drawing it right here. We already have the machine for L1 and a machine M2 for the language L2. I'm going to kind of make use of those again. Okay. I'm going to have a one start state. I'm going to be kind of clever. I could go ahead and try to make something that does this, think about all the things we need to worry about. But I'm going to go and do something really lame because I am really lame. And it's going to go ahead and have a start state. From the start state, I'm going to have two transitions, both epsilon transitions. One is going to go to machine 1, the machine I had for language 1, and the other one is going to go to the start state of the machine I had for language 2, M2. Okay. There we are. Let's go ahead and show it there. So, yeah. So I'm going to start with this non-determinist. My start state goes here, has two epsilon branches to each of the two machines I had both up. So how does this machine accept a string that ends in A? It makes a lucky guess and says, I'm going to take the epsilon transition out of the two that I can take. I'm going to take the two that lead to the machine that accepts all strings ending in A. Okay? And likewise, I'm going to lead to all, or I will guess it's a string that begins with A, and I'm not even going to look at it, I'm going to guess. And then again, if there's some way to guess correctly, I will accept it. Notice if a string does not, if it begins with B and ends with B, there's no way for this non-deterministic machine to accept. No way I'm going to accept if my string is, say, the string BB, or BAAAAB, or whatever. So it's not that I'm accepting all strings. There are some strings I simply cannot accept. even with those epsilon guesses there. Okay. So, okay. Yeah, so I could also, we're going to go in the next lecture is going to be saying, hey, how might we go build something for this? And we're going to think about a deterministic machine for L3 and then use the finger method and use that to build something. I'll leave that as an exercise for you to try actually. Build a deterministic machine for L3 and then use the finger method to sort of say, hey, can I go ahead and have some make some of these choices non-deterministic, and do that. And then we're going to go ahead and do that here. I'm going to use the finger method for this whole thing. Well, not quite. We're going to go through that later. I'm sorry. So this is a more complicated machine that uses these epsilon transitions. I'll just show this. Here's a spoiler. This is the regular expression that matches what this machine accepts, and it's kind of hairy. It's kind of a hairy machine. I will notice in here that there's a couple of transitions we don't really need. It says the transition from Q4 to Q7, Q4 to Q7. It says this arrow, we could actually get rid of it and still have an equivalent machine. Why is that? If you're in Q4 and you want to take a C, consume a C and get to Q7, oh, I can do it here. I can consume a C, go to here, then take from Q2, take an epsilon transition to Q7. Yeah, that also gets me to Q7 without consuming only the letter C. So, by the way, I'd call those, if I took this arrow and just omit it, I'd say it's a different machine because it's has one less arrow, but it has the equivalent language. So I'd say it's an equivalent machine because it accepts the equivalent language. Okay, I'm going to take a break here and we'll come back with another video.